Welcome to the submodule 2 of 4 on terminology and directional calculations. In this submodule, we are going to cover the differences between the different survey methods most commonly used to calculate a directional survey and state which method is most commonly used. Let's take a look at the main survey calculation methods used in wellbore trajectory design and analysis in the oil and gas industry. Accurate directional surveying is absolutely vital, not just for hitting the geological target, but also for avoiding collisions, minimizing tortuosity, and optimizing well placement to improve production. There are 4 primary methods used, but of these, only 2 are still commonly used. These are average angle method. This method improves accuracy by using the average inclination and azimuth between 2 survey stations to calculate the path. It's a middle ground technique, offering slightly better precision than the tangential method, but it's still not suitable for complex 3D trajectories. Minimum curvature method. This is the industry standard today. It calculates the shortest possible curved path between 2 survey points, giving a much more realistic trajectory. It uses dogleg severity and applies correction factors to improve accuracy, especially important in extended reach drilling or when trajectory control is critical. We will look at how to calculate the average angle method, then build this up to a minimum curvature method. Now let's focus on the average angle method, one of the foundational approaches used in wellbore trajectory calculations. In directional drilling, accurately calculating the 3D position of the wellbore is essential for several reasons: hitting the reservoir target, avoiding collision with adjacent wells, and ensuring proper well spacing for production optimization. The average angle method offers a relatively simple yet effective way to estimate wellbore position between 2 survey points. As shown in the diagram, this method assumes the wellbore path between 2 stations can be approximated by a straight segment using the arithmetic average of the inclination and azimuth angles measured at the 2 ends of the interval. It then applies basic trigonometric relationships to compute the change in coordinates, north, east, and true vertical depth. Mathematically, we calculate delta, or change in the north component, equals delta MD times the sine of the average inclination time by the cosine of the average azimuth. Delta east equals measured depth times by the sine of the average inclination times the sine of the average azimuth. Delta vertical depth equals the change in measured depth times by the cosine of the average inclination, where delta MD is the measured depth between survey stations. While the average angle method is an improvement over the basic tangential method in terms of accuracy, it still assumes a straight line trajectory, which might not represent the actual curved nature of a borehole, especially in high dogleg severity sections. That said, it's still used in many field applications, particularly when processing historical data or in wells where trajectory changes are relatively mild. In modern operations, especially in complex extended reach or horizontal wells, more precise methods like the minimum curvature method are typically preferred. But the average angle method remains an important concept, simple, fast, and useful in early planning or for quick calculations when high precision isn't critical. Let's break down how we calculate north displacement, one of the essential directional components in a well path. North displacement tells us how far the wellbore has travelled in the north-south direction between 2 survey stations. The process starts by identifying the vertical section of the triangle formed by the trajectory using the change in measured depth and inclination angle. The first step is to compute the vertical section using the formula vertical section equals the change in measured depth times the sine of the average between the start and finish inclination. Here, we take the average inclination between the 2 stations to get a more realistic estimate of the borehole trajectory. Then, we calculate the north displacement delta north. The change in north displacement equals the vertical section times by the cosine of the average of the start and finish azimuth. This method assumes a straight path using average angles, which is typical in the average angle method, commonly used in earlier drilling phases or low dogleg wells. In field operations, this calculation helps visualize how the well is progressing relative to the planned path and assists in real-time directional decisions. Precision here ensures efficient reservoir contact, avoids costly sidetracks, and improves production performance. In the history of wellbore surveying, several calculation methods have been used to estimate the position of the drill bit. These methods, now largely retired, range from the crudest to the more refined. The tangential method is the simplest. It assumes that the borehole continues in a straight line at the last measured inclination and azimuth. While quick, it is highly inaccurate and often overestimates displacement. Interestingly, geologists still use it today for rough approximations. The balanced tangential method improved on this by averaging the inclination and azimuth between two survey stations, producing a more realistic path than the simple tangential approach. The Mercury method, famously used in the Apollo space program, introduced more sophisticated mathematical corrections for wellbore curvature. Although rarely used in drilling today, it represented a leap forward in precision during its time. Finally, the radius of curvature method assumed the well path between stations followed an arc of a circle. This provided a much more accurate representation of borehole position, and it became the industry standard until more advanced minimum curvature methods were developed. These methods illustrate the progression of survey techniques as drilling evolved, highlighting the drive for greater accuracy and reliability. Now we'll take a look at the minimum curvature method, which is the most accurate and widely accepted method used today for calculating wellbore trajectories in directional drilling. This method fits the well path between two survey points to a curved segment of a sphere, specifically the arc of a circle that connects those 2 points with the least curvature. It assumes a smooth and continuous path rather than a straight line, and introduces a correction factor known as the ratio factor or dogleg severity correction factor. This factor ensures that the curvature is scaled properly to maintain geometric accuracy. Unlike simpler methods like tangential or average angle, the minimum curvature method accounts for both the change in inclination and azimuth, making it ideal for extended reach and horizontal wells where high-precision trajectory control is required. This is particularly important when navigating complex reservoir structures or avoiding collision in multi-well pads. Mathematically, the beauty of this method lies in its precision. It introduces no mathematical error, meaning that, as long as the input data is accurate, the resulting 3D coordinates will faithfully represent the true path of the borehole. That said, the real world introduces its own complications. As noted on the slide, although the algorithm is flawless, human and equipment limitations can cause deviation. For example, drill string flexibility, formation changes, and tool inaccuracy can introduce small trajectory variations known as micro-tortuosity, which aren't always captured in surveys. Nonetheless, this method is the industry standard because it provides the most realistic and reliable representation of the well trajectory. It's used in most modern directional drilling software and is essential for wellbore positioning, anti-collision modeling, and optimizing reservoir contact. Now we're going to look at how the minimum curvature method is calculated. The method assumes that the well path between two survey stations follows a section of a circular arc and not a straight line. This curvature is defined by a central angle called beta or dogleg angle, which is calculated using both the inclination and azimuth at the start and end of the interval. The formula for beta is shown where the value is calculated in radians. Once beta is known, we apply a ratio factor f to scale the path appropriately. This correction factor compensates for the non-linearity of the curve. If beta is less than 0.25 radians, the ratio factor approached 1 and the curvature is minimal. Once the ratio factor is known, we can use the average angle method and apply the ratio factor to get the minimum curvature result. These calculations give us the change in position between 2 points, which can be integrated across the entire well to build an accurate 3D well path. The illustration on the right side of the slide shows how the minimum curvature method fits a smooth arc between two survey points using the measured depth and angular data. You can see that it avoids the jagged, unrealistic transitions that might occur with simpler methods like the tangential or average angle approaches. The minimum curvature method delivers the best balance between mathematical accuracy and field practicality, making it essential for modern directional drilling programs. Now let's try an exercise where we apply the minimum curvature model. In this example, we have two surveys separated by 100 feet. What is the dogleg angle? In order to do this, we need to apply the formula for the dogleg angle. The first step in calculating beta is to convert the inclination and the azimuth angles from degrees to radians. A radian is the arc length divided by its radius. Therefore, if the circumference of a circle is 2 pi r, then in radians it is 2 pi. That means 360 degrees is 2 pi radians. 1 degree must therefore be 2 pi divided by 360 degrees of pi divided by 180 degrees. So to convert from degrees to radians, we must multiply by pi and divide by 180. To apply this to our example, the initial inclination converts from 15 degrees to 0.2618 radians, and the initial azimuth converts to 0.4363 radians. For the second survey point, the inclination converts to 0.4363 radians, and the azimuth is 0.7853 radians. Now, refer to the worked example on the slide as I will work through it. First, let's apply the formula for beta or dogleg angle. The best way to do this is to break down the different components of the equation, calculate these, and then calculate the full equation. So the first component of the formula is the inclination change, which is the cosine of the second inclination minus the first inclination. This is 0.9848. The second component is 1 minus the cosine of the azimuth change. Then multiply this by the sine of the initial inclination times the sine of the second inclination. This is 0.0066. In an example like this, be aware that rounding errors can have a big impact. Then compute the dogleg angle in radians. The answer should be 0.2091 radians. Now, in order to present the answer in degrees, we need to convert back from radians. So apply the conversion, which is 180 times by pi, which should give you a dogleg angle of 11.98 degrees. Let's take a moment to look at the relative accuracy of different directional survey calculation methods. In this example, we assume a theoretical well drilled from 2,500 to 2,600 feet measured depth, with a dogleg severity of 3 degrees per 100 feet. That translates to an inclination change from 15 degrees to 17 degrees, and an azimuth change from 20 degrees to 28.13 degrees. These changes represent a fairly typical directional adjustment over a short section of a wellbore. Using this scenario, we compare three common survey calculation methods to assess their accuracy in determining true vertical depth, TVD, and north displacement. Looking at the table, we see the average angle method produces an error of minus 0.004 feet in TVD, but a significant 1.436 feet in north displacement. The radius of curvature method is slightly better for north displacement at 0.065 feet, but worse for TVD at negative 0.047 feet. Finally, the minimum curvature method, often regarded as the industry standard, yields zero error in both TVD and north displacement in this theoretical case. In directional drilling, accuracy matters, especially in complex trajectories or when trying to hit a small target zone. Errors can lead to missed objectives, inefficient reservoir contact, or even costly sidetracks. That's why minimum curvature is the preferred method in most modern directional software. It provides the best approximation of the actual well path by assuming a continuous and smooth curvature between survey points, unlike the linear assumptions of other methods. This comparison underscores the importance of choosing the right calculation method for accurate wellbore placement and efficient reservoir development. In this submodule, we have covered the differences between the different survey methods used to calculate a directional survey and state which method is most commonly used. From this, we understood how to calculate the average angel method and the minimum curvature method, and that the minimum curvature was the preferred method for accuracy. Please complete the quiz before moving on to the next submodule. Thank you.